Welcome to Math 104, where we're talking about Chapter 5.2, Logarithmic Functions and Properties. So what I want you to do before we start with 5.2 is take out your 5.1 notes, the very front sheet where we looked at the graph of your exponential, and we're just going to compare that graph with the logarithmic graph that we'll be getting to here in a moment. So first off, let's take a look at what a logarithmic function looks like. Now, typically it has the setup of y equals log with a base b x. So this b is considered the base, and this x is the value that we're evaluating. Number we will be evaluating. Now this number here, log base b of x, is going to be an actual number. So we can't really separate those two. We can't multiply, add, subtract, or divide those two values either. They are actually going to represent a whole number in itself. Now how we actually can say this is log base b of x. So in case you're going through your homework and you're like, how do I say this? Or you're trying to explain it to somebody else, we can just say log base b of x to describe that. Now this looks an awful lot like the exponential function that we came into contact with in 5.1, where we said it's f of x of b to the x, where b this time is still your base of the exponential. And then it is raised to the variable. Raised to a certain power. And just like your logarithmic function, right, over here, this in itself is a number, or is a value. Now, the reason why I want you guys to look at your logarithmic function graph along with your exponential functions is that we're going to see some sort of mirroring happening. So logarithmic functions are considered inverse functions. So that means the opposite function of exponential. So in our case, we saw in our graph last time, the graph went up like this. So notice that we have some sort of mirroring effect go on. So with that mirror comes some nice tidbits, right? So unlike last time where we had a horizontal asymptote at y is equal to 0, right? The opposite of a horizontal asymptote is actually a vertical asymptote. At x is equal to 0. So we have a vertical asymptote at x is equal to 0. Now see if you can spot some other special features of this graph. So an x and y intercept, a domain and range, and keep in mind we are just kind of doing the opposite of what we did from your graph before. So your x-intercept, last time in your graph, we did not have an x-intercept because of this asymptote. This time, we actually can clearly see an x-intercept, which means the y-intercept, we don't have one because, again, of this vertical asymptote. Keep in mind your y-intercept is where your x value is a number and y is 0. And in our case, your y value, right? Oh, so sorry. I flipped that around. Your x is 0 and your y is some number. So you'll notice that x being 0 is still that vertical asymptote, which we cannot cross. So you will not have a y-intercept. Now your domain, for that same reason, right? We're approaching this line here, your graph is trying to approach where x is equal to 0, but you can't cross this vertical asymptote, so we're never going to achieve 0. So we can get very, very close to 0. So that would be our smallest number. And our graph then goes all the way out towards positive infinity. Our domain last time was all real numbers. There's no restriction for your x, it just continues. Whereas your range for your logarithmic function, right, we're starting down low towards negative infinity, and then we're going to go out, but we're also going to continue upwards of positive infinity. So this one would be all real numbers. So you'll notice that on those graphs, on those x, y intercepts, domain, and range, that we've actually reversed all of those values. Now, taking a look at your graph here, your x values are not able to be negative. There are no negative x values for logs. No negative x values for logs. And that is clearly shown in your domain. Notice that we kind of start as close as we can to 0 and then go upwards. So that eliminates any sort of negative x being placed into your logarithmic function. So logs cannot be negative. You will see an error on your calculator if you try to insert a negative into your logarithm because it is just not allowed. Now we're going to take this interesting inverse property and we're going to use it to solve some of the more complicated logarithmic and exponential functions. Now, before we launch into a problem like this, where you say, okay, well, 2 to the x power is equal to 32. Well, we don't know what x is quite yet, so we're going to have tools in a moment to figure that process out, right? So let's do something a little easier. So it says 2 to the x is equal to 4. This can be broken down as just saying 2 times itself, how many times will get you equal to 4? Well, we can write, and the process to do this, if you're not seeing it, is to change 4 to have the same base as 2. So 2 to the what power is equal to 4? How many 2's do you have to multiply until that happens? Well, 2 squared is equal to 4. So that just means 2 to the x is equal to 2 squared. So that means x is equal to 2. Let's try it again with another problem. 5 to the x is equal to 125. So 125 can have a base of 5. So how many 5's do you have to multiply by itself to get 125? Well, 5 times 5 is 25 times another 5 will get us to 125. So this just means x is now equal to 3. I don't know why I wrote this down there twice now that I'm looking at it. So if you're noticing that on both sides of the equation that they can be made into having the same base, we don't need the logarithm rule. So try it again on your own for this one. How many 2's do you have to multiply to get up to 32? Got 2 to the x on one side, 2 to the what power? So 2 times 2 is 4, times 2 is 8, times 2 is 16, and times 2 is 32. So we have 5 2's here. So that just means x is really equal to 5. So now what we're going to do is work on your, let's see. So these ones, I already gave you the answer to this middle one. And this one is not the right one. 64, 9, okay. So let's have you pause the video and try A, B, and C. I know B, we already gave you the answer, but see if you can work it out just a little easier. Okay, so 4 to the x. How many 4s can make 64? Well, that would be 3 4s. So x is equal to 3. Okay, we already know the answer, but that's okay. 3 to the x is equal to 3 squared. So x is equal to 2. And let's try it again here. 2 to the x is equal to 8. So 2x is equal to 2. Well, how many 2's can make 8? Well, 2 times 2 is 4, and another 2 will make 8, so that is 3. Now, if you're not loving this process, there is another process. We can actually go ahead and rewrite these expressions to contain a log. Right now, all of these expressions here are in exponential form. You have your base of 5, 2, 4, 3, right? And it's raised to a certain power or raised to a variable. Now, what we can do is actually put it into a logarithmic form. Now, why is that necessary? Well, if we were going to be asked to solve the following, 2x is equal to 31, well, we know that 2 to the 5th is equal to 32, and 2 to the 4th is equal to 16. There's no way of getting to 31 easily. So that means your x value, this value right here, must not be a nice whole number. So what we're going to do is convert your exponential into a logarithmic function. We can do this by using the following property down below. This just says, and we actually went from the other way, we can kind of go either way. If we go from an exponential into a logarithm, right, what we're going to do is called the swoop method. And I'm going to write it down here. B to the x is equal to y. Now, if you don't like the swoop method, there is another one, which I'm going to show you, the one that I kind of prefer, but some students really like this one. So it says to start on your base. First, locate your base. Where is it? Well, the base of the exponential is right here. You always start on your base. Now, what you're going to do is you're going to come from your base up and around the y value here. And the y is going to be on that side because there's an equal sign. And then you're going to land on your exponential. Now, the order in which you write is the order in which you swoop. So notice that we started on your base. You came up and perhaps you touched y or came very close to y. So that's going to be the second thing you write. And the last thing you write is going to be x. Now, I'm not a huge fan of the swoop method because a lot of students forget to write the word log. We're going from an exponential into a logarithm, so you need to write log. So log, and the first thing we write is the first thing we started with, your base. Then we said the second thing is the very next one, y. And then we can have an equals to sign because we're still hoping to get some value out of it, is equal to that third thing, x. So you go 1, 2, and 3. If you wanted to, if it helps, you could say maybe this equal sign is 3 and that's 4. That's all right. But I'm hoping that you do this enough practice that you can just put equals in that. Just do not forget to write the word log. So let's see this in action. So if we have 2 to the x is equal to 31, what we're going to do is, again, start on your base of 2, up and around 31, perhaps you touch 31, and then you land on your exponent of x. Don't forget to write the word log. Now we have to write your base. What is your base, or where is your base? Your base of the exponential is 2, so our base is going to be attached to your log here, 2. Notice that it's kind of underneath the log. It's a smaller number. Your next value that we write is 31 is equal to x. Now, I did tell you there's one other method if you're not a huge fan of this, or if you might be a forgetful individual. I definitely am at times. So an alternative method, if you like it, just going to rewrite the expression, is to actually go ahead and write the logarithm with the same base on either side of the equation. Now, what that's going to look like is I'm going to write log, and I'm going to match the base of the exponential. So our base being 2, I'm going to write a 2. What you do to one side, you do to the other. So I'm going to go ahead and write that same thing on the other side. Now, this time you're not matching 31 because this is not your base. I need these two numbers to match. This base here has the exponential. Now, what we don't know yet and why we don't know it is it's a rule. It's going to come in probably about 10 minutes or so, is that when you match your bases, they kind of undo each other's processes, just like this mirror, right? It's an inverse property. That's why we get to do this. So they end up canceling out just on one side because they match, and your x value drops. So x is equal to log base 2 of 31. The same exact expression you have on the other side. Now, the reason why they the reason why they cancel is that if you take, for example, x squared, right? Well, how do you undo a square, right? Well, you take the square root of it. And I won't get into the nitty-gritty of saying, okay, you have to do the plus minus. For right now, we're just taking the square. So one value squares it and the other square roots it. So something like 2 squared under a square root, right? Well, 2 squared after taking it is 4, and then the square root of it is 2. So they cancel each other out to get that same value, very much like you have here. So let's try it again one more time. And I do believe we're going to get some practice with that here in a moment on our very next page. We don't, but I'll make a couple examples. So let's practice this one. 2x is equal to 8. Now, either practice your swoop method or the taking the log, so writing the log on both sides. I'll kind of show you both. Sorry, there's a fly in here. So swoop method, we said start on your base, come up and around, and land on your exponent. Now let's say that this 8 was written to the other side. You're just going to swoop to the other side. If that feels unnatural, then rewrite it and put the equal sign on the other side. So we have the word log. We're matching your base to 8 is equal to x. Or if you like writing it the other way, 2x is equal to 8. We said, okay, well, we're going to take the log. We're going to match the base. If it's 2, ours is 2. Do it to the other side, log, and we're still sticking with the base 2. We are not doing 8. That is not your base. Your base of the exponential is 2. They cancel out on one side, only one side. Your x values drops. We have log base 2 of x. Now I'm going to give you just a couple more to practice. So actually, why don't we practice on the other ones right here? So A and B. So if we're taking 4x is equal to 64, I'm going to write the log base here. So log, and this time we're going to match the base. Instead of 2, this one has a base of 4. So we're going to write 4 underneath. It cancels on this side and your x value drops. So we have x is equal to log 4 of 64. If you were to type that into your calculator, your answer would come out to be 30. Let's try it again here. If we have 3x is equal to 9, we're writing the word log on both sides. And this time your base happens to be 3, so we're going to match that 3 to both. It cancels, and your x drops. X is equal to log base 3 of 9. If you wanted that swoop method, I can certainly show you on this one, which was going to be my plan, and then that went out the window. You come up and around, and you're writing log 3, then the 9 is equal to x. Okay. So now let's take a look at going in the reverse. So you have the logarithm. I see what I did with my notes. You have a logarithm, and you're going to go backwards. So in our case, right, log base b of x is equal to y. We can still certainly swoop. So starting on your base, as always, this is your base here. We start on your base. We come up and around y and land on your x. Your x is kind of acting as that exponent as we had last time. And again, the order in which we write is the order in which we have come up to swoop. Now this time, because it's an exponential, we do not need to write the word log. This one is a lot easier. Students don't mess this one up nearly as often because you don't have to write that word log. So instead, you have the base b, that's the first thing you write. Then you have the second thing, y, that you write. That's going to be your exponent, is now equal to your x value. Just make sure that your bases are the exact same value. That's where you always want to start. Now, you certainly can do it the other way as well. So if we were to rewrite it, just like we did last time with writing the log of an equal base, this time you get to actually write the same exact base that you have. So in this case, if our exponent is b, or sorry, our base is b, then we are going to take the b of both sides. Now, just like last time, we said, okay, well, if we have x squared and we square root it, right? The opposite of that is to have the square root of x and now square it. So for example, the square root of 4 squared, right? Well, the square root of 4 is 2, and then you square it, it's going to be 4. So again, just another opposite action, just in a different order. So b and your logarithm of b, that is going to cancel on that side, and x drops. So then we have x is equal to b, and then y is up above in its exponent. So let's take a look at some examples. Can you practice the next 3 for us? So if we have log 3 of 81, notice that there's nothing on this side. You can put a question mark, you can put an X. It's just saying, hey, we want to know what this comes out to be in the future. And let's say for right now, we don't know how to enter these into your calculator. So we can certainly swoop, starting at your base of 3, coming up and around X and landing on 81. So this just means we have 3 to the x is equal to 81. Now we're going to figure out now, with the skills that we had from our last page, 3 multiplied how many times by itself gets you to 81? Well, 3 times 3 is 9, times 3 is 27, times another 3 should be 81. So we really have 3 to the x is equal to 3 to the 4th. So x is equal to 4. Now, the other method, if you didn't like the swoop, I'll show it here to you again, which again, this is the method that I tend to prefer, right? If your base is 3, we're going to write the 3 just under. So these cancel, the log and the 3 cancel. Your 81 drops, so 81 is equal to 3 to the x. All right, let's try it again. Now right here. So again, question mark or an x. Now this time, instead of the swoop, I will just show you that base one that I like to do. So again, our base happens to be 3. Do it on both sides. We cancel. And this drops. So 1 over 27 is equal to 3 to the x. Now this one we are still able to do. Because think about if we just had 27 is equal to 3 to the x, right? Well, what would your base be? How many 3's do you have to multiply to get to 27? Well, 3 to the 3rd is equal to 27. So in our case, this would be x is equal to 3. Now, this isn't our original equation, right? We have 1 over 27. This is a reciprocal. So if it actually is going to have a negative exponent. Now, if you haven't seen the video on the negative exponents, please take a look there. This will be kind of in brief, but we have a rule that just says if we have, let's say, I'll start with the first one. If we have a to the negative x, or sorry, negative 1, we don't typically see negative exponents. And so what we're going to do is we're going to shift its location. So if it was in the numerator, we're going to bring it down below, and maybe I put a number out front. We're going to put just this value down below. So we're going to keep everything else the same, and we're just going to shift the position of A. By doing that, we now have a positive, positive exponent. Now the reverse is true, right? If you have a, and let's say to the negative 1 here, if you see a negative in the denominator, again, you're going to shift its position, only that value. You're going to shift it back up to make sure it has a positive exponent. So in our case, if we have 27 down below in the denominator, it's a little hard to evaluate it like this. It was much easier when it's up by itself in the numerator. So if we shift its position up, we now have 27, but now with a negative first exponent. Your exponent down below here is just a positive 1. That's why we don't see it. So when you shift its position, it now has a negative exponent. Now we can do all the exact same things we did to the to it. So we know that 3 is going to be its exponent. Oops, I'm so sorry. I was supposed to write a 3. We have a negative 1, but keep in mind, this is still to the 3rd power. And we learned back from 3AT or chapter 3 intro that we have a power raised to a power. So we're going to actually multiply these two powers together. So negative 1 times 3 is really a negative 3. So this just means x is equal to negative 3. Now your last one. If we have log 0.001, if you're not a huge fan of decimals, we can always convert this into a fraction. This is in the thousandths place. So we can make this into 1 over 1,000. So if that helps, that's great. Now notice that there is a log missing, right? The base is missing. Now this was absolutely intentional. This is a special base. Special logarithms have a base of 10. Or sorry, not special logarithms. Common logarithms have a base of 10. So if you see a logarithm that's showing a base 10, it can be written as just log of x. This is what your calculator is going to do if you just hit that log function, because it's already written as a base of 10. So if you want, you can put your base 10 here, and then we can take the same base to both sides, or you can swoop, up to you. It cancels on one side and allows this to drop. So you have 1 over 1,000 is equal to 10 to the x. So again, taking the idea that we learned from that log base 3 of 1 over 27, see if we can apply it to here. We have 1,000 in the denominator. Let's bring it up. 1,000 to the negative first power is equal to 10 to the x. Now, how many 10s do you have to multiply to get to 1,000? Well, you have to multiply 10 3 times to get to 1,000, and then multiplying those values or your exponents together. So x here is equal to -3. We're going to get some more practice here, or I'll show you a couple of examples at the very least on how to practice this very rule. Now, with special logarithms, common logs have a base of 10. There's another logarithm out there that has a base of e. This one is called natural logarithm. Natural logarithm. Typically, if you have log base e of x, this is usually written as ln, logarithm natural log of base e to the x. And even more common, you're not going to see the hidden e. So typically, you'll see ln of x along with just log of x if it has one of those two bases. Now let's take a look at typing these into your calculator. So if we have something like this, log of 12, right? Well, what is your base here? Well, your base we just talked about, if it's not written, it's really 10. And there's no need to shift it around because we're going to be using your calculator. So let's round to, looks like 3 decimal places, and find log base 10 of 12, and again, log of 22. So we'll do log of 12 here, rounding to 3 decimal places, is 1.079. And I'll do it one more time, but in decimals. We'll do, I believe it's function. So go over to function and hit log, and then go back to the main screen, and we're going to evaluate 22. And you'll notice it pops up over on the right-hand side. It's 1.342. Now I do want to pop over back to your scientific, your graphing calculator, the TI-84. I kind of just jumped right into it. If you're having a hard time finding the log, it is located right next to the 7 on the left-hand side. .079, and we said 1.342. So notice how awful those numbers are coming out as opposed to the ones that we have seen before. They come out kind of clean. Now let's try it again, but with some sort of negative inside. So log of -5, if you're using this TI-84, make sure you hit the negative button that's located between the enter and the decimal button. Now notice that this is coming up with a wild answer, right? That means something is wrong. And if you look over at this, the very, very right side, beside the 8 is an I. This is considered an imaginary number. An imaginary means not real. It actually does not come up. If you're using and I think I have it programmed for a certain mode. It has it in real. If your calculator just comes up with error, then that's okay. This number really does not exist. Let's see what it does with your Desmos calculator. So we have a -5. There you go. It says undefined. So keep in mind, we said at the very beginning, we said logs cannot be negative. So we can just write undefined. Okay. So just a few more examples. See if we can rewrite these two examples, but in its opposite form. So write this one, since it's already in your exponential, write it in a logarithmic form. So go ahead and pause. All right, so we have e to the y. So this one, or sorry, this value here has the exponential that has the base. So we're going to have to match its base. So by matching its base, keep in mind, because it's an exponential, we're going to have to write something, right? Typically, we write log of that same base. However, we just found out that if we have a base of e, we really have ln. So we're going to write ln of base e on both sides. Ln of base e on both sides. That will cancel and allow this value to drop here. Y is equal to ln of base e of 2x. Let's try it with this one. Notice that you have the logarithm, no base is showing, x is equal to 2. So what is your base here? Again, see if you can pause the video. Well, your base, if it's not written, we said, okay, well, if it's not showing, it's really a common log. It's a base of 10. So we can write a hidden 10 here. And what we do to one side, or sorry, we can match the base of 10. And what we do to one side, we do to the other. This allows us to cancel on one side. X can drop. So x is equal to 10 squared. So x is equal to 100. Now let's say you are a huge fan of your calculator. Totally get it. If you don't like this process, that's fine. You will have to kind of use this process because as you're seeing, some values are variables. But if they do come out that you have a series of values, or sorry, numbers like the log 5 of 7, what we're going to have to do is called the change of base formula. This allows you to evaluate logs of different bases. Because on your calculator, we just said, hey, your calculator uses a logarithm with a base of 10. So in our case, if your calculator is an older model, you're going to have to use this equation. It just says log base a of b, where a perhaps isn't equal to 10. Then we're going to write the log of this first value above over the log of your base below. So if we were to try that again, but with the ones below it, it would look like log, and we said it's your value that's over here that comes above, so that would be 3 over log of your base 2. Now what's happening here, why we're allowed to evaluate it, is that because we don't have your base written here, they're really both in the base of 10, something that your calculator is capable of doing. So if we put this into, I guess, oh, not here. If we put this here, right, log of 3 divided by log of 2, closing your parentheses. Notice that by just hitting the log button, that is the base of 10. So you have 1.585 if we're rounding to 3 decimal places. Now your TI-84, if you use this app or if you have a newer model, does have the ability to negate this change of base. It actually has a capability of putting in a base that is different than 10. So go over and hit the math button. This is under that green alpha button. And we are going to go all the way down until we see log base. Go ahead and hit that one. And then we're just going to write 2, which was your base, and then 3, and then hit enter. And notice that it'll pull up with the same exact equation. Now, if you're not seeing it here, that just means your calculator is a little bit older. The app has it. Newer models of TI-84s have it. If you're using a TI-83, that unfortunately does not have it. Let's try it again here. So let me clear that out. We said we have, let's see. We have a fraction. So we'll do log here of, what was it, 3, close parentheses, over log of 2. And that'll do it. So again, it pulls that same one. So now let's see if our logarithm, if we can actually go ahead and change our base by using this value. And let's see, is there a subscript value? I'm still getting the hang of no, I don't think there's a way to do it. I'm still getting the hang of your Desmos. I don't think there is a way to insert a change of base. I'll look into it though. I just can't remember what I did in a previous video. I do not believe Desmos has that capability. So you're going to have to do the one above if you want to evaluate. So pause the video, see what you can come up with for the remaining 2. Okay, so we get to evaluate. Oh, that's what we're doing. We're evaluating. And I'll show you here in the change of base. We said log of 5 or base 5 of 7 is 1.201, or sorry, 09. And then I'll do the last one in Desmos, where I'll just change these values, 31 and 2. So 4.954 would be those values. And again, I'll kind of just write, just in case you did need the change of base. If your homework is asking specifically for the change of base formula, and it has like 2 spots for one for the formula and one for the solution, it's just looking for this first part. Okay. Now let's take a look at a few properties down here, some that we have kind of come up with already. So if we're looking at log base b of b to the x, right? Well, notice you have a logarithm with an exponential, right? An exponential, even better, with the same exact bases. So when your bases match, we just said we can cancel and they're allowed to drop. So this is just equal to x. So let's do it again. Pause the video, see if you can get that one. These 2 values match, or your bases match, I should say. They cancel, your 2 drops. It's just equal to 2. What about this one? All right, well, ln has a secret base, we said, of e. So your e matches with your exponential base. They cancel, and your 3 drops. Now the last two are just the exact same, but they're written in a different format. Just think about whether you take the square root first or the square, right? So in our case, we now have an exponential with the base b raised to a logarithm with the equal base. So do they cancel? Yes, they do. They cancel, and it allows to drop. So try it again here. They cancel, and they drop. This is only done when they are the exact same bases. Now, what you're going to do, my advice is as you're going through, when in doubt, just use the swoop method, use the same base method. So taking the base of whatever it is, whether it's a log first or an exponential, take the base to the same side and see what you come up with. Now, I'll make a side video of just kind of practicing a few of the ideas that we had here today in case that you need a little bit extra. Otherwise, there are more videos out there on YouTube. Please see the Canvas course for some additional support videos, lectures, articles, Khan Academy, things like that.